Hi, everyone. I hope everyone's having a great day so far. There's been lots of good talks, and it's my sort of official first time in Calgary. I've only been to Calgary once, but it was for like a day meeting, so this time I'm actually here for 3 days. Hopefully I get to check out the city a little bit. This talk is about container security. The title, Do Containers Fully Contain Security Issues? Trying to have fun with words there. Who am I? Farshad Abbasi. I'm based in Vancouver, Canada. I'm the co-founder of Mirai Security. I'm also CTO, CISO of Mature Technologies. It's a small software startup building a services platform. I'm also an instructor at BCIT, which I guess is similar to SIAT here. I've been teaching network and information security there for 15 years, and a few other courses that I've built security over time. I'm also a news correspondent with a local radio station in Victoria, CFAX AM 1070. Get to talk about security issues when they come up. I'm also a board member of BSides Vancouver, so I organize this with my other fellow board members in Vancouver. So some of you should come check it out if you get the opportunity to. We have a nonprofit society called MARS, Mainland Advanced Research Society, where we curate different community events from talks to social gatherings and things like that. And I guess fun fact about me, I'm an avid music fan. I probably have one of the largest record collections of most people that I know. It spans all kinds of genres of music, and that's my hobby. But enough about me. This talk is about container security, but we're going to start by looking at cloud computing, because containers are a form of cloud computer or virtualization. So we're going to look at that just to make sure that we're all level set and we understand the different types of cloud computing and where containers fit. And then we're going to really clarify what containers are, because I noticed that in this journey of me with containers, it's been about 2 years now, that there's a lot of confusion. People call Kubernetes containers. There's a lot of confusion of what's a container, what's a scheduler, what's orchestration, what are all these different things. So I'm going to try to clarify that so then you have a better idea of where everything fits. And then supporting cast, which is all the tools and various things that support container deployments. And then we're going to look at the difference between containerization and virtualization. There is a fundamental difference there. And the two example container engines that I use for this presentation are Docker and Garden. Docker is probably the most popular one. Garden was one that I ended up using. I was a principal architect for HSBC. I worked there for quite a while, and we had implemented Cloud Foundry's Garden, so I'm familiar with that. So those are the two commercial technologies that I picked for this presentation to kind of compare them a bit, fairly similar. And then we're going to look at key security concerns with those container technologies in general. And then, of course, quickly look at some known vulnerabilities. And then everybody wants to know, well, you've told us all about the security concerns. How do we do something about it? So that's how we wrap it up. We talk about what is considered safe container practice. You do have to keep in mind that this technology is still fairly new. I mean, it's containers in that form, they've been around for a long time, but in the modern form, not so long. I've done this presentation. This presentation started about 2 years ago as my journey with containers started, and it's evolved quite a bit since its early days. There's a lot that's changed in terms of security. It's gotten better, which is good and hopefully expected as we really jump into the world of containers. So we'll talk about that a little bit as well. So here you can see a picture of the Vancouver's Lion Gate Bridge, and Vancouver's always cloudy, so computing in the cloud, I figured that was a very fitting picture to put that there while we were talking about the cloud, because it's always cloudy and raining, and I think when I left there was a massive downpour as well, so cloud computing fits Vancouver very well. The definition from NIST is cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, e.g. networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interactions. A lot of words, right? But I wanted to put the official NIST definition of cloud computing while we start talking about this and level set our understanding. And there are different models, and the different models of cloud computing, they all require workload isolation. So how you do that workload isolation determines the model of cloud computing that you go with. So you can do physical separation. You can have bare metal cloud where one machine, you can have multiple physical machines and you're allocating workloads, but your workload isolation is the physical machine. So there's only one workload per machine. The only advantage that gives you is a bit of dynamic control over that. But most of us are familiar with the virtualization concept, also known as hardware virtualization, and that's your typical IaaS. You'll see VMware and all that kind of stuff. And so that virtualization is where each of those virtual machines, they have their own kernel, right? It's not a shared environment, that sort of thing in that sense. And that's typically used to provide IaaS or infrastructure as a service. And the vulnerabilities there, they're related to CPU or hypervisor that can be impact, right? Because the bottom line is that hypervisor, the host OS, is shared. So that's where the attacks could take place. Then you have containerization. So as you go up the stack, also known as OS level virtualization, and that's where your workload isolation is your the operating system, and that's used to deliver container as a service, CAS, which is a newish term that's coming up, or PaaS. Some of you may be familiar with that. That term has been around for a number of years, platform as a service. We'll talk about this a little bit. And then at the top of the stack, you have the multi-user accounts, which is, what's SaaS. So the workload isolation there is actual user accounts, right? So there's not much separation aside from that. So here you can see from top to bottom, right, you got the bare metal, and then the people that are usually involved there with bare metal or IaaS, they're infrastructure architects or admins, right? So the lower you go, the more control you have, right? Because particularly with bare metal, you have the whole hardware. You can install and do things as you wish. And the higher you go, the less control you'll have, right? So when you get to SaaS level, you don't really have much control. You have a user account on the system, but someone else is running the database, and they're running all the other stuff underneath it. So, and PaaS is somewhere in between. So people that are typically involved with PaaS are the application architects or developers. That's where the focus is, because everything, the other components are provided to them, right? Like the database logging service and all the other services are provided by the platform. So really, you're just building an application. So that typical user of a PaaS is an application architect or developer. And then when you get to SaaS, it's just end users, because there's not much to do but configure the SaaS application, given the parameters. You're not writing the application. You're not doing anything with the platform. It's all provided for you. So what are containers, and why are we talking about them? So containers, as I mentioned, also known as operating system level virtualization, they provide multiple isolated user space instances that share a given kernel, right? So we're going to look at what these user spaces and namespaces are in a second, but each instance is essentially a container. And it's also known as partitioning or virtual engines or jails. For example, in FreeBSD, we had FreeBSD jails, or the Chroot jail has been around for a long time. How many people have heard of Chroot or have used it in the past? Okay, a few people, right? That's pretty good. I mean, I've used Chroot for at least since, the late 90s, with Linux. We used to, when we hardened our applications, you would Chroot them and put them in their own jail. But it isolated it, but mostly from a perspective of a file system, right? It didn't really isolate the process space or many of the other spaces. And that's where modern containers have really built on that concept and added a lot more isolation. Of course, the Linux kernel has evolved and provides the facilities for you to do that isolation and a few other things as well, along with the evolution of the container technologies. They typically encapsulate applications and act as the interface to the surrounding system for that application. And the kernel provides your resource management. So it limits the impact of the container activities on other containers, and that's what provides that facility. So here's Chroot. It's been around since version 7 Unix and from 1979, so it's, the concept of containers is nothing new. I find that a lot of these older concepts are coming back in more modern ways, right? Everyone is probably in here uses Slack. I mean, Slack is a glorified IRC, in my opinion, and containers are glorified Chroot, essentially. I mean, all these things, they're going back and saying, hey, what technology is left, and how can we modernize them? And then they're picking them up and modernizing them and doing a pretty good job with most of them, right? And Slack is really good. Docker, these things are really good, way better than their previous incarnations. So Chroot, what it did, it only isolated the file system view for process and its children, but didn't isolate other resources. So, for example, your networking processes, et cetera, weren't isolated. You could see the process. If you did a PS, you could see the processes for everybody else that was running on there. So it only helped if someone was within that Chrooted environment, and they couldn't see the root of the file system, right? The root that they saw was the root that you wanted them to see. And so they couldn't pivot around and do that through the file system, but the other resources were not separated. And then the root account also had full view and access. So modern containers, they use namespaces, and this is the key. And how well they use it, it depends on the implementation. And they use that to separate the resources. So The namespaces that are typically supported is the PID namespace, which is for process IDs, right? Most modern container technologies support isolation there. The mount namespace, the network namespace, the UTS, which handles host name and NIST domain name, and IPC namespace, and the user namespaces. The user namespaces are arguably the most important one, and it's not always implemented. I'm going to talk about that in a minute, so just kind of keep that in mind. But that's one of the Docker, for example, implements it, but it's only optional. It's not enabled by default. So, in my opinion, it should be enabled by default because that's a big contributor to security. There are other things that modern containers use as well, things like C groups to meter and limit resources, to provide some access control to devices and perform crowd control. Where are we going? What's happening here? There we go. More on namespaces. So the user namespace is the most important one that I wanted to talk about first. They're namespaces for user IDs and group IDs. So a given user ID inside the container will map to a different user ID on the host if the user namespaces are enabled, right? But if you haven't enabled that, it'll be the same. So if you have a root user in one container, it'll be the same root user ID in all the other containers, including the host operating system. And as you can imagine and appreciate, that's not a good thing, right? So if you have root access in one of those containers and there's a vulnerability and someone breaks out with root access of a particular application, then technically, because you're sharing the kernel, they could make kernel calls with that same user ID, which would then they can break out of that and go to other containers. So what you want is enabling the user namespace separation, and so that the root user doesn't map to the same root user ID as the one in the host, right? But if you don't have that enabled, then it's the same ID all across all the containers, and that's not a good thing. So when I started looking at containers a couple of years ago, for example, Docker didn't support that at all, so that was a big negative for them. Cloud Foundry's Garden had some support for it, but it wasn't perfect. And even with support for it, the implementation has to be really good, because even if some of the container technologies that do support this, there have been known vulnerabilities where you can still break out of it. So it's kind of a tricky one. Because it's fairly new, there have been known vulnerabilities at the start. System calls and security logic should be namespace aware and check the capability in the correct namespace. So see, this is kind of tricky, right? So even if you've implemented it, if the system call is not namespace aware and it's not checking the capabilities in the right place, things can still go wrong. And so incorrect checking may lead to, there's the clone new user and clone FS exploit vulnerabilities. And so exploits are still possible, even if you enable this, right? So don't think that I've enabled it and everything's great. Maybe the implementation is not right. Maybe the person making the system calls is not doing it correctly. So it's not all that straightforward. And what I've seen is when I worked with development teams that aren't security aware, they just see the benefits in containers. They're so light, they're so great. You can deploy them so quickly. It's perfect for DevOps, but they really don't think of the consequences. So what they do is a lot of people are re-architecting their applications from traditional applications where they contain many functions, and they're breaking it into containers, or they're breaking them into microservices, and then each microservice resides in a container. But then they're mixing and matching all these different applications in one pool, right? Whereas in the past, each application resided on its own physical server, separated from the other application. So if there was a vulnerability in there, the impact or the blast radius was more limited. Now they're throwing all these microservices belonging to different risk types, right? So you've got applications of different risk levels. All their microservices are in containers. They're all running in the same cluster, right? And so if someone breaks out, there could be impact on the other one. So you really have to be careful about segregating and how you architect your application as it coexists with the other microservices from other applications. We'll talk a bit about that later. So other namespaces, there's the network namespace. It provides a separated network stack for each container, right? That's what namespaces are about, is separation of the particular type of resource that you're talking about. So if you've enabled and implemented network namespaces, it will provide a separate network stack. It's widely used. There's been abuses. So for example, the net raw, because you need raw sockets, and there's been an abuse where there's a flaw in that particular namespace. And you can't really say, well, you can't use raw sockets, for example, or not use net raw. So there are problems there as well. There's the PID namespace, which is the process ID namespace, which allows each container to have a fully isolated process tree. So unlike Chroot that didn't do that, you can see other people's processes. The process ID would be different inside each container than on the host, but again, vulnerabilities, there have been vulnerabilities that have shown that this info can also leak. Again, none of these are perfect yet. The technology is still evolving. The other namespaces that we have are the mount namespace, which is used to separate the file system for each container. And there's the IPC namespace that deals with the System 5 IPC and POSIX message queues, and there's the UTS one that I mentioned that's used for host names. So these are the ones that are typically implemented. There are actually more that some containers may or may not implement, but most of the modern ones do those, again, may not do them perfectly. Aside from namespaces, there are other Linux security features that can be used to secure the containers even further. One of those is the use of C groups or control groups, right? And what those do, for those of you not familiar, they limit and account for and isolate the resource usage. So, for example, your CPU usage, your memory usage, disk I/O, and that kind of stuff. So they provide that resource separation. And for a collection of processes, and they can also be used along with IP tables to do some traffic shaping if that's what you want to do. There are also capabilities that you can use, and the Linux capabilities allow for breaking down the root role into more granular pieces. So instead of just saying you have root access, and root access you can do all these other things. With the Linux capabilities, you can say, no, you can only do this one privileged function out of all the things that root can do. So you can actually make it more granular and have more control. There's also Mac mandatory access control, which it limits the action of a program. There are hooks provided by Linux by the LSMs or the Linux security modules, such as AppArmor, for those of you who are familiar with it. Both Docker and Lexi have this enabled, and SE Linux is also an option, but it's not well supported and documented. But again, things will probably change as we go forward. You can also use seccomp to filter system calls, right? So if you want to, say, hey, I don't want just anybody to be able to call these, or I want to have some sort of filtering on what systems calls can be made, then you can put it in strict mode, which allows only a small set of system calls, and which can't be modified, or you can go in filter mode, and you can write these filters using BPFs, so the Berkeley packet filter programs that allow more finely grained policies. Docker supports seccomp BPFs, and there was a ptrace vulnerability that bypassed this that was demonstrated as well. So, okay, we looked at capabilities and different things you can do to secure containers, but what about container uses? So container uses are things like allocation of finite hardware resources, same thing you would do with hardware virtualization, with VMware and all that kind of stuff. They give you improved hardware independence and added resource management, so you can package an application and its dependencies in a container and just, without dependency, just deploy it out. Again, virtualization has done this for a while as well, like with VMware. Or OVF files. You can also, a big use for containers is hosting APIs and microservices, right? So as the people are re-architecting their applications and taking these old monolithic applications and breaking them into microservices, and providing access to those microservices through an API, containers go really well with that. So you can take a microservice, put it in a container. It's light. Microservice is small. I mean, it wouldn't make sense if we did this with hardware virtualization or with an actual VM, because if you broke the application into, say, 50 functions and put each of them into a VM, that's too heavy, because each of those VMs are going to have a kernel, and now you're going to end up with 50 kernels that you have to start up, and it requires a lot of resources and all that kind of stuff, right? But if you take the application and break it into 50 microservices and put them in containers, they don't have their own kernel. They're light. They start up really quickly, so it's not as much of a burden. So that the application breakdown that you've introduced due to putting them on microservices doesn't add a lot of overhead if you use containers to do that. And then, of course, each of them can be opened as an API. But the thing to note is that if you have a microservice, it doesn't necessarily have to have an API, right? I mean, some people think that automatically if I have a microservice, it has an API, but it doesn't have to be that way. You can have microservices that talk to each other without APIs, or utilize the resources in other ways, or communicate. So containers also help automate deployment of applications. So there's distribution method for software to guarantee reproducibility. And like I said earlier, they're good in the DevOps tool chains for deploying and testing code. And they're typically the building blocks for PaaS. So when you get into the PaaS conversation, typically containers are a building block of that, amongst other things within a PaaS. So Cloud Foundry is a PaaS, and the container engine used in Cloud Foundry is Garden, and we'll look at that in a minute. And they're common in virtual hosting. And then I put security at the bottom, right, with question marks. So is that a container use, right, or is that a byproduct of it? Because some people are like, well, now I'm taking my application, and all these functions used to be together in one, and now I'm separating them, putting them in separate containers. Isn't that better? Isn't that isolation, right? But that's like telling me back in the late 90s that, hey, I've got a switched hub, and that gives me security because people are no longer able to talk to each other. But as we know, that's not true, right? Because you can do ARP poisoning, you can flood the ARP table. There's lots of ways to get around that and put that switched hub into regular mode and read the data that's floating around. So, or VLANs when they first came out, right? Like some of these things were not designed to address security. They were designed to, separate the network traffic and reduce the chatter and all that kind of stuff. Security was a byproduct. In the beginning you could do VLAN hopping and all that other stuff. But as we've seen with technology like VLAN, as the years have gone by through process and improvements in technology, then we can implement those kinds of things in a secure manner. But security was not, it was more of an afterthought of that, right? So it's the same thing. Containers were not just really designed to give you security and extra isolation. They were designed to be lightweight and do all this other stuff. But if you implement them correctly, they can end up in giving you some added security. But the operative word being here, deploying them correctly and that sort of thing. So here are some modern implementations. They make containers easy to use. Docker is extremely easy to use. Like, it'll take you a couple minutes to install it on your computer. Download the thing, click, it's installed. Not so much for Garden or Cloud Foundry, a little bit more tricky. But they have definitely come a long way. Docker, so there's things like Docker Engine, Cloud Foundry's Garden, OpenVZ, Lexi, all that other stuff. Some of them are designed to run multiple processes and services, some only a single service, right? So some of them run one service, so it's like the traditional, pet. There's the pet and kettle concept, right? Kettles can scale out. Pets are these things you grow, and they're just like a single machine. So you can use containers to run a full-blown machine like you would with any other virtualization technology, or you can use it to run a single service. So that's typically when we get to microservices, right? So in that mode, you're putting a single function or microservice into a container, or you can put a full-blown application stack with everything in it, just like a virtual machine. Because at bottom line, when you're inside the container, it looks like a regular operating system, right? So you could be running whatever you want in there. What about the supporting cast? So these are all the different tools that support the container engines, right? So container engines being, things like Docker Engine or Garden, but then you need orchestration, you need all this other stuff. So there are things, container schedulers, they allow scale out, load balancing, adding storage or network resources, maintaining high availability, recoverability. That's things like Docker Swarm. Docker Swarm is fairly new. Before Docker Swarm, if you wanted to do scheduling, you would use something like Kubernetes, right? Because Docker Engine itself, there's not much. Some people would use Ansible and try to make it work. Chef, Puppet, all kinds of other stuff. But Kubernetes came along and they're like, hey, we can do all the scheduling and orchestration for you really nicely. But now Docker's got Swarm as well, which it's actually pretty cool because before Docker Swarm brought the concept of clusters, right? And before that, you didn't really have that. So what you did is you deployed all your containers into one big pool. And as I mentioned earlier, that's not really so good for security. That's like saying, our company is going to have a flat network, right? No DMZ, no sub networks, or nothing. Let's just put everybody in one big network, right? That's the best analogy I can give you. But with Docker Swarm, you can create clusters, and you can label. You can, in your developer pipeline, you can introduce tags, and then you can based on the tag, you can deploy containers on different virtual machines, and then your separation barrier becomes the hypervisor rather than the shared kernel, which is where the container sits. So you get some added security by doing that, by deploying. So you say you have like 3 different risk levels, and you tag your applications, risk level 1, 2, 3, and when you're deploying them through your pipeline, that container gets deployed into different clusters depending on the label that you've attached to it. So then you're creating separation amongst the containers. That's one of the uses of clustering, but there's many other uses for it as well. But that's from a security perspective, and you can do that as well with Cloud Foundry. They have the similar concept. They call them elastic clusters, and you can set up multiple elastic clusters, and you can deploy containers into different clusters depending on what you're doing, the risk level, and however you've architected your system. So Cloud Foundry does that. Their orchestration of scheduling is called Diego. Kubernetes, Kubernetes supports Docker containers or Docker Engine containers, and then of course there's Swarm. Then there's the packaging and staging, right? So there's the OpenShift's S2I, and there's the Cloud Foundry build packs. Those are the more popular ones. Then you also, underneath the containers, you need some sort of IaaS, right? I mean, containers are up here. You need to run them on top of something. It's either bare metal or some sort of hardware virtualization. Typically, you run them on top of some sort of IaaS. And so you need to orchestrate that. So typically, Ansible is the most popular one. So that's how you orchestrate your virtual machines on top of which you deploy your containers. And Cloud Foundry uses Bosch. So Bosch deploys the virtual machines. And then once you've got those virtual machines, then Diego comes in, which does the scheduling and automation and all that kind of stuff for the containers. So hopefully that makes sense, that how these things come at different levels and how they play out together. In terms of platform as a service, you have things like OpenShift or Cloud Foundry. So Cloud Foundry brings it all together. So it includes Diego and Bosch and Garden and all this stuff, and logging and database and all the other facilities you need to have a PaaS, and then puts that together that you can build an application on top of. There's also OpenShift that also provides a PaaS. And so these tools have evolved at the same time independently. So there is a bunch of crossover. There's a lot of confusion. Some of these people don't talk to each other, and this market's fairly new. So none of this is sort of cut and dry that like, this does just this. Some Kubernetes might do some scheduling, but it might also do some other stuff. And Cloud Foundry does multiple different things. That's because these things have been evolving independently over time. But as time goes by and as this ecosystem matures, we'll see some of these things settle down. Some players will go away. Some of them will grow and absorb the others. And in 5 years from now, this won't look the same. I mean, if you look at hardware virtualization, I mean, VMware has been around since the early 2000s, so it's almost like 17 years that it's been around, right? So that's quite a bit of time for it to have matured, addressing security and tooling and all that kind of stuff. And whereas with modern containers, it's only been about 5 years or so. So we've got a way to go. But it's good. It's very exciting. Lots is being done in security, and that is a good thing. So quick look at the difference between containerization and virtualization, because I know that this is not always clear. So in containerization, containers always share the same kernel, right? So on your host, when you install Docker or Garden or whatever it is, if that's a Mac or if that's a whatever Linux flavor, you'll only be able to, all the different containers that are running, I mean, that's the kernel that you're using, right? If you say on that computer you install a virtual machine and then in that VM you deploy containers, again, those containers will be sharing the kernel from that virtual machine that you've deployed, right? So they all, whatever is the host, they will all be sharing the kernel with that host. So they are fast, so you can't use containers with different operating systems, right? Like as I mentioned, so if you've installed Docker on a Linux machine or a Linux VM, those containers will all be Linux containers, right? If you want a different one, you have to set up a different VM with, say, Windows kernel, and then you can deploy containers that will go in there. Containers are faster, they're lightweight, they're more portable, and they scale more efficiently. Why is all this? Because there's no hardware emulation, but then the sharing of the kernel has something to do with it as well, right? Because if you don't have to boot a full stack every time, that's going to be really fast, right? Like when you're firing up a VM, I mean, it's fast if you've got an SSD especially, but the thing is it still has to go through the full process, start the kernel, do all that stuff, load the full OS, and then you're in. But when you start up a container, the OS is already there. It's sharing the kernel, all that stuff is there, the libraries are loaded, all it's doing is just loading that top part of the stack. So it's much quicker, much more lightweight. And that's what's attractive to the development community that wants to really quickly do that continuous integration and continuous development and roll something out and test it really quickly. And this lightness really lends itself well to that. They don't provide the same level of isolation as virtualization, right? Obviously, I've been saying this over and over. You're sharing the kernel, so there's not as much the same level of isolation. It's not that everybody's got their own. It's like one brain and multiple people sharing that brain. If that brain gets diseased, all the people sharing that brain will share the disease, right? So if you have everybody's got their own brains, every separate kernels. If one of them gets sick, it doesn't impact the other one. So that's the danger of containerization, and that's why you have to be really careful when using it. Virtualization, on the other hand, is mature. Like I said, it's been around for quite a while, over a decade. Extensive ecosystem, allows for mixed kernels. I mean, each VM has got its own kernel on the same platform. The host emulates the hardware provided to the VM. So there's this hardware emulation, which makes it a little bit slower than containers. And it looks like it's running on separate hardware from the perspective. And the hypervisor is the security boundary, right? So that's where it comes, that's where if you break out of the hypervisor, and there have been known vulnerabilities that have demonstrated that you can break out of a hypervisor, but again, the technology's matured and hopefully that will happen less as we go along. Here's a quick graphic just to demonstrate that. There's a type 2 hypervisor, right? It's not the bare metal, where you've got the server, you've got the host OS. So it's like a typical, you had a laptop, you're running Windows or Mac on it, then you put a VM workstation as your hypervisor, and then you got a full stack, right? Each of those have their own guest OS, they have their own binaries and libraries and their own apps, right? But on the other side, here you've got the server and your host OS, whatever it may be, Mac or Windows, but then there is no hypervisor. You've got the runtime, like you'll have the Docker runtime, and then that runtime is using the kernel of the host kernel. So whatever your machine had, right? If you had a Mac laptop or Windows machine or whatever it was, that's the host OS. So the runtime is using that, and everybody's sharing that kernel. Now you can see that there's the orange one on the left, the first two containers, they're sharing binaries and libraries. So you can have some containers that, again, for efficiency, that share libraries and binaries. So there, the 4 on the right and the 2 on the left, those 4 on the right are sharing some libraries, and the other ones are sharing some other libraries. But other than that, there's a shared kernel down below over here. So let's look at a little bit of the behind the scenes as how what the Docker architecture looks like. And then we'll look at the quickly behind the scene of Garden, Cloud Foundry as well. So it may be a little bit small from the back there, but you can see here we've got the container accesses the Linux kernel virtualization in many ways, right? So if you've got the Docker runtime up here, to access the Linux kernel virtualization facilities, you can do it through libcontainer, libvirt, Lexi, etc. So before version 0.9 of Docker, Lexi was the default execution environment. But then what they've done is after 0.9, they're using runc, which is now standardized, or also known as libcontainer, which is written in Go. It's open source, allows for direct use of Linux virtualization facilities, but they still support abstracted virtualization interfaces. So although this is natively supported, they still support the other interfaces as well, or I should say Docker does. So actions, so typically things you do are done to the Docker base image. So it uses UnionFS, so the layers are created. So the Docker images, there's a base image and you can put layers on top of it. So it's an interesting way of doing it. And it allows for recreation. So you could recreate the layers by putting things back together. And the other thing to note is that the Docker daemon runs as root. So this may or may not be a good thing. As you can see the architecture here real quick. So you can see, basically there's your, again, it may be too small at the back, but you got your Docker daemon up here. And the Docker daemon, you can talk to it, it exposes a bunch of APIs, right? So they provide a command line interface. That command line interface, all it's doing is just talking to that API. I mean, if you picked up that API, you could even run your own interface to it, right? But they've provided a command line interface that talks to that API already. And then you can do things like build, pull, run. And so when you say, let's say, for example, if you do a Docker run and the image is not there in your local repository, what the Docker daemon will do is it'll go to the registry out there somewhere and says, hey, Farshad's trying to do a Docker run on this one image and I don't have it. And it will download that to your local image repository, and then it will create an instance based on that image, right? So either you have that already or you don't, and if you don't, it will go and get it for you, and then it'll create the container instance. So here we've got 4 different container instances based on that image. And then this is the swarm architecture. So we got 2 clusters here, as you can see, this one cluster and one cluster. So before swarm, all these containers would have been in one cluster. There was no separation, right? But with swarm, basically you can say, hey, I want these containers to go to this side, and I want the other ones to go here. And again, you can do this based on labels and tags, and you can architect it based on your requirement. And there's cluster managers that manage each of the clusters. This is only showing 2 clusters, but as you can appreciate, you can have a lot more than that. So what about Garden? Let's have a quick look at that. Very similar architecture. All these things typically they have a daemon, so this one has a Garden server. So Garden used to be called Warden, and then what they did is they rewrote it in Go. So the W got dropped, and then the G from Go got put in, so Warden became Garden. And so what they did is, as a part of the rewrite, they also added this flexible backend, so that this is not all, in the previous versions, this was all together. So the server and then the Linux backend were together, but this allows pluggability. So you could actually take the Linux backend and put, say, a Windows backend or some other backend and easily adopt Garden for different operating systems. And then the client works in a similar way. There's an API that the server exposes, and when you're running the command line to it's calling those functions to the API, to the Garden protocol. And then, as similarly as you saw with Docker, the daemon spawned off the, it basically looked at the repository and then picked up an image and it created a container instance based on that image. And similar thing happens here. The Garden server, they have build packs. It's not images, and it's not layered. They don't use UniFS. It's a little bit of a different thing. But the Warden shell daemon will launch the instance, and then the app will run inside. And you can see there's multiple containers here that are managed by that. So then the communication between the actual containers is done through the back end, and that's specific for different operating systems. So here's a bit about it. So Garden, it was Warden, rewritten in Go. It's got pluggable backends for platforms, as I showed you a second ago. There's the Run C backend, which is Linux-specific implementation of the Garden interface. They're using that Open Container Interface, OCI standard, which is good. AppArmor is used for all unprivileged containers, and then seccomp is used for whitelisting, which restricts access to the set of system calls, which we mentioned earlier. The Warden shell daemon that you saw in the diagram on the right side there, what it does is there's a root process for managing containers, right? So when you want to actually manage the container instances, that's done by the Warden shell daemon, and it streams standard output and errors back to the client for troubleshooting and other. This is now really small, so I apologize, but this shows the whole Cloud Foundry PaaS, right? So the Diego here, this is your container orchestration, but a PaaS is more than that, right? So here is where your there's your Garden engine, right? And then the containers are being launched here. So they call it in Cloud Foundry, they call them a cell. So you've got these Garden cells, and that's where the containers are running, but Diego is doing all the scheduling and orchestration, and the PaaS is providing a database, is providing Loggergator with logging capabilities, routing capabilities. So it provides a multitude of services as a platform, but within that, the key component of it is the containers themselves, which are put into what they call Cloud Foundry cells that are managed by their orchestration engine called Diego. Quick comparison between Docker Garden, fairly similar, minor differences in terms of resource isolation and control. As you can see, they both do CPU sharing. Garden does memory swaps and network bandwidth and disk size quota. Docker does CPU sets, memory swap, block device bandwidth. In terms of dynamic resource management, Docker doesn't support it. Garden supports it, but it's not used that often. Image management, the Garden uses build packs, so it's whole images, but you can use them, you can reuse them to create new ones. Docker's got the layered approach where you can build upon it using UniFS. Can you link the containers? No, Garden doesn't let you do that. Like build packs, Docker has flexibility, again, due to the nature of how it deals with the images. And exposing ports, you can expose multiple ports per container in Garden, but and also with Docker. So we've talked about all these things of what they are, where they fit, and all that other stuff. What about key security concerns? What are they? So I've mentioned this one, the top one, user namespace support. Again, when I started this presentation a couple years ago, only Cloud Foundry supported this, and it wasn't great. Now Garden supports it as well, and a few others. But it's not enabled by default in Docker, so if you are deploying it, make sure you enable that. And without it, processes running as root inside a container can have root access everywhere, right? Because it's the same ID. They're not mapping it, and they're not creating different IDs in each container that map to a unprivileged user in the host operating system. And it has to be configured properly and not break programs. And as I mentioned in one of the earlier slides, the program also has to be aware and use the right namespace and put things in the right place. So it's not straightforward. It's like trying to implement TLS in your own application rather than using something that's provided. I've worked with a lot of developments that were creating native apps, and some of them had to implement their own TLS handshake and all that other stuff, and they got it wrong most of the time. It's not straightforward, and it's a similar idea here. Namespaces do not cover everything in Linux, so there is more to than just the namespaces that you saw. So even if they implemented those, even if they did it perfectly, there's more to it just than those namespaces that you saw. Again, that's another gap. There's also the whole imperfect design and code. So not everybody's perfect. There can be a lot of issues when they're building these things. They're complex. The kernel itself is got a lot of opportunity as an attack surface. So imperfect design and code increases the attack surface. There can be namespace leaks present in many containers. Many containers have had little security analysis, right? When I teach my security course, one of the things I tell the students is that, in security, it's really important to have stood the test of time. There are a couple of important criteria. Like one of them is get your, code reviewed or your idea reviewed by as many people as possible. Get as many sets of eyes looking at it, right? Because the more sets of eyes looking at something, the more problems they'll find, and hopefully you'll fix those problems, and then your stuff gets better, right? That's one of the arguments for open source. They're saying, hey, you put it out there, lots of people look at it, they can fix all the problems, right? Whereas with closed source, it's only the eyes of those that are privy to be looking at it, and that's not as many as a generality. And the other principle is having stood the test of time, right? So as the time goes by, more problems would have been found, the technology's perfected, but this hasn't had that chance. Containers are fairly new, they haven't really stood the test of time, and so we've got a bit of ways to go. Do some more security analysis and find some problems and address them, hopefully. And also Docker's image verification is not 100%. There have been known problems with that as well. The shared kernel is a big one. Any vulnerability in the kernel can impact all the other containers, right? As you saw, it's just one host OS and a runtime, right? You don't have each VM in its own box with its own kernel. It's just one. So if there's any problem and one of them breaks out, it can go through the kernel and go elsewhere. And so the operating system kernel provides much more functionality than the hypervisor. That also means a larger attack surface, right? Because the hypervisor is really locked down only to do a very specific set of things. But Linux kernel is general operating system kernel. So it doesn't minimize its exposed functionality. It's like in the old days, one of the things that made Cisco successful is that they said, why take a general operating system, right? Back in the late 80s, if you wanted to get a router, you had to go get a Sunbox, right? You got a Sunbox, ran Sun OS, and it was a full-blown operating system, but most of the world's internet was routed using these, Sun OS boxes. But that's a full-blown operating system. Why do I need all these facilities, all these services? Who is service and finger service and a million other things that comes with Unix, right? So what Cisco did is like, hey, let's take the Unix idea, throw out all the other things you don't need, and just keep the bits that are to do specifically with networking and routing, right? And then made this like very lean Unix operating system that became the Cisco router. And so it's nothing crazy. They didn't build, yes, they built their own operating system, but based on existing concepts. But the core concept was throw things you don't need, keep just what you need, and minimize that. So it's going to be faster, plus you don't have all this extra bits that increase your attack surface, right? Same thing when you're like setting up, in the old days, I remember when setting up a Windows server, heaven forbid, it came with like a million different services that, so one of the things you did as a hardening process, you went through it and you're like, why is this service on? Why is that on? You disable all the services, deleted all the accounts you didn't need, and you reduce the attack surface, right? So that's the same idea here. You've got a kernel. It's a general purpose kernel. It's got all these facilities that it's providing for other uses. It wasn't designed just to facilitate containers, right? And that those extra things that you don't need to use for containers can provide opportunity for attackers to break out of containers. So the point here is that they were not designed to contain security issues, which was the title of my presentation. They were designed to do other things, but we can use them to try to contain security issues. There's also the issue of covert channels. Some of you are familiar with this being security, but if you're not, they provide capability to transfer information between processes that are not allowed to communicate, right? So you say, hey, I've physically separated these two processes. There's no IP, there's no mechanism of communication. But hey, if they both have access to the same memory, one of them could hit a particular block, and then the other one could observe how many read and writes are happening, or open a particular file. If they both have access to a particular file system, one of them could open the file and close it so many times, and the other one could observe that file to see what's happening, and they're almost sending each other out-of-band signaling. And then with today's computing power, you can do that pretty quickly, so you could actually transfer information across those covert channels. So there's the storage channel example that I just talked about. You can communicate by modifying a storage location, or you can do the timing channel attacks, which you perform operations affecting response time. So the receiver observes that, and then based on the observation made on the changes in time, you can pick up what the message is. So it's difficult to completely prevent on the same processor, right? So if you're sharing the same processor or the physical resources, some of these things are difficult to get around. That's just the inherent nature of how things are. And techniques for locating potential covert channels are things like analyzing the resources of a system or doing source code level analysis, but you can possibly be reduced by careful design and analysis, but it's hard to do that. So here's the rowhammer attack that came out a few years ago. It was a defect in hardware protection mechanisms, and computer hardware is pretty complex. So the DRAM rowhammer bug was used to gain kernel privilege access, but it enabled changes in value in other programs in kernel, and it was demonstrated by the Google team on a variety of systems, right? So basically, you changed the voltage repeatedly in a row of memory cells, and if there was an observer watching what was happening, then they could pick up a message. Just a quick slide on known vulnerabilities. There have been a whole bunch. There have been since 2014. These are from the CVE details. That's where the source is. They basically go through the CVE database and present you with lots of metrics on these kinds of things. So since 2014, they've been tracking Docker vulnerabilities, particularly just focused on the Docker engine. If you look up other things to do with Docker, there's actually more vulnerabilities, but I focused on just the core engine, so there were 14 of them, and they range from all kinds of things from DOS and code execution and being able to bypass something, gaining privilege, and so on and so forth. And for Garden, there have been 11 since 2016 that they've been tracking this, so I guess 2016, 2017. There were 4 in 2016 and 7 in 2017. Again, this is just the core piece. If you look at Cloud Foundry as a whole, there's more. I mean, if you step back and look at CVEs for Cloud Foundry and all the tools and things that comes with it, there's probably more than 11. But that's eye-opening, right? So they're not all perfectly safe with zero vulnerabilities. There are things being found. At least, you can see average 2-3 vulnerabilities a year. And hopefully as time goes by and these technologies mature, that will go down. But I wouldn't foresee that for the next couple of years. So how do you contain the potential harm, right? So these are called containers. So how do we actually, how do they live up to their name? One of the things I've mentioned is you should group containers on a given VM based on classic segregation principles, right? As security professionals, some of us are familiar with this concept. Like I said, in network design, right? You typically either go based on a department or based on function. You look at all your users and you go, hey, this is my accounting department. They're going to be handling financial data. I'm going to create a separate network for them, right? And these guys are my sales guys. They're going to download every email and click on everything and open all the stuff. So they're really risky. I'm going to put them in their own network. And this is my Wi-Fi network. I'm going to separate that because I have guests coming into it maybe. And this is my DMZ where the servers sit. You create all these separate network segments. You put rules between them. So why not do that for containers, right? And the Docker Swarm plus Diego's facilities provide they provide you with facilities to be able to do that separation. So you can use a risk-based approach, use whatever approach your organization uses to do separation, but apply that classic methodology and consider impact and likelihood when you're doing that, right? So if you put a bunch of containers that have the likelihood of something bad happening, but the more of those things you put together, the likelihood rises. There's a point at which it doesn't make sense to combine containers of different types because then the likelihood goes to a level that may be beyond your appetite, and you may not want to add more containers of different types in that mix. Services should be run as unprivileged, right? As you can appreciate, this is one of the top things I've talked about is the user namespaces. So if you're running privileged containers, there's a chance of breakout. If you haven't implemented namespaces, then you're really in trouble. So if you run them as unprivileged and you've got the user namespaces enabled, then things are better for you. And privilege should be dropped as soon as it's not needed. That's common sense. And you should treat root inside a container as if it was root outside the container, right? That's important. And only run containers from trusted parties if you can. And follow a layered defense approach. Use AppArmor or SC Linux, right? I mean, the layered defense approach, keeps coming back. On Monday we all heard about the Wi-Fi attack and all that stuff. And of course, when I worked at a financial institution, they required us to always use a VPN no matter where, right? So they gave me a laptop, and the laptop, you opened it up. The first thing it did is connect to the network. The second that it did, it automatically connected to the VPN, right? You couldn't use that laptop over Wi-Fi or wired network without the VPN if you were not inside the organization. And that's your layered defense model. So if the Wi-Fi security fails, when they've got the VPN, if that fails, their applications are using TLS on top. So you got 3 layers of security, right? That's the whole defense in depth or layered security approach, and you should follow that here as well. You have your segregation, you put your control groups, you implement the capabilities and all this other stuff. And then if one of them fails, you've got access control, you've got all these other security mechanisms to really back you up. So that's where things like AppArmor or SC Linux are important to also look at, not just the segregation through clustering. You should standardize and verify hardened host OS. That's pretty important because the host OS is the main kernel that's offering itself to everybody else. So that should be standardized and hardened, because if it's not, then you have a chance of breakout. You should scan containers for vulnerabilities, right? I mean, most of us that are going to use containers, it's going to go in some sort of a DevOps environment. It's going to go in a continuous integration, continuous delivery environment. So why not, as you're rolling these things out, implement some sort of a vulnerability scanning and patch management in that dev pipeline? So as these things are being rolled out, when the developers are pushing out a new thing, hey, what version of it does it have? What version of OS does it have? Does it have the latest patches, and so on and so forth? And check for configuration. And you should measure containers and sign them. Analyze them, sandbox them, build profile, confirm the signatures of boot. All these sort of security practices should be applied to containers as well. These are not new practices. And monitor and detect anomalous behavior. So definitely this is, again, security best practice, not just limited to containers, but doing your alerting and logging and all that other stuff is quite important here, as it is with other use cases. And of course, analyze the usage logs to see if there's weaknesses or there's some patterns that you should adopt, and then sharing the learning across different instances within your organization. So that brings me to conclusion of today's talk. Conclusion is containers are really useful, right? Don't be like, oh no, they're not good for security, let's not use them. As with any new technology, if you use it correctly, there can be a lot of benefits. So they're very useful. They help ease software management. Great for your development, especially if you're going and doing a re-architecture of your applications as microservices. They really come in handy. Work is being done to address security, right? Like lots of work has been done in this space. As I mentioned, just in the last couple of years that I've been involved, I've seen a lot of security features come on board. Implementation of user namespaces is one of them that wasn't really done before. But you should use it with caution, right? This stuff is still not perfect. Processes in the container should not be given privileged access. They're good for deploying apps that are trusted. So if you have apps from the same development team or same vendor, that's fine because it's the same trust. But if you're mixing and matching things from different people and not clustering, then you're putting yourself at risk. And there's other mechanisms such as SE Linux, SecComp, AppArmor, and separate user accounts should be used in conjunction with all the other controls that we mentioned to ensure that you have a safe container ecosystem. So that brings me to the end of this talk. I'll open it up for questions, as I'm sure some people will have. Yeah, put your hand up if you have any questions, and I'll be happy to answer. Yes? The question was, are there unique tools that will provide visibility of container to host communication? I am not aware of anything unique. In terms of looking at it outside of an IP boundary, right? IP to IP communication, you can do that, but in that respect of intercepting it at that level of the kernel communication, I'm not aware of any specific tools, but I'm sure there's some work being done in that area. There was another question there. To reduce the privileges on the runtime, that depends on the implementation, right? So Garden and Docker have done a fair bit of work. The thing is, Docker still runs as root, so that's not good. But I know Garden is working on that. There are complexities because sometimes the runtime actually needs privileged access, so they try to limit that through those other mechanisms that I was talking about, through limiting the system calls and a few other things. But directly, it's not an easy problem to solve. Any other questions? Yes?
Is there kind of a law of diminishing returns that after a certain point, there's a certain container count on the host because you actually have to have more of some things, like you now have to monitor each individual container. So at some point you're actually taxing the host more so, depending on the level of insight that you need on a per container.
Because you have so many machines. I think so. If I understand the question correctly, is there a level which is just not optimal because you have so many containers, you have to monitor them, and there's a lot of overhead, right? Is that the question? Yeah, and that's true. So even though containers are lighter and they don't have their own kernel, there's still a bit of that overhead because you're firing up this ecosystem and you have to manage it. But it's not a lot. If you think about it, the heaviest part is the kernel itself and the libraries, right? So if you're sharing that, above it is just it's the user namespace separation, and that's handled in the kernel. So it's not super intensive because the kernel natively supports, through the various interfaces that you saw, built-in support for namespaces. So that separation is being handled at that lower level and it's done very efficiently. So by just saying, hey, I want a network namespace and give me, ETH0 and 3 different namespaces, that doesn't add a lot of overhead. So that's what's really attractive about them. So you can fire up quite a few of them, but there will be a point where it's diminishing returns, where when you fire up more of them, then there's just too many. So how many is too many? That depends on the application you're deploying in it, whether it's a microservice or whether it's a full-blown application, and you'd have to analyze that within your environment. There will be a point where you're like, okay, on this one VM, I can't put more than 50 microservices, but that depends on what that microservice is doing. So the focus is more on the requirements from the application perspective, how much resource memory and all that kind of stuff they'll need. Any other questions? Any other questions? Yes, yeah, absolutely.
Is there any work being done on the kernel itself to address the unique requirements of containerization?
Yeah, well, yeah. So that's what you saw. The lib container. There's a bunch of the Linux kernel modifiers. So the facilities that the containers use are provided by the Linux kernel. So that base is provided by the kernel. For example, the namespace separation, control groups, and all those kinds of other things. Oh, for containerization. Well, if you have like support for lib container C or run C or whatever, that would be the flavor that would have that support versus the ones that wouldn't have that. So you just compile that in, or you use that version that has those libraries in the facilities, yeah. Any other questions? How are we doing for time? I think we've got like 10 more minutes. Cool. Well, if there are no other questions, I'll stick around if people want to come and ask questions directly or talk about anything. And thank you very much for attending, and have a great afternoon.